specific latent heat. So last week, we studied the idea that different substances take different amount of energy to heat up or increase in temperature. So for example, some substances might take over 4,000 joules just to increase the temperature by 1 Celsius for 1 kilo of the substance. And then other substances like, metals usually need less heat. So for 1 kilo of a metal, you might only need 500 joules to increase the temperature by 1 Celsius. And so we studied the idea about specific heat capacity. Now, while that's very useful, however, there is something that we need to take into consideration that we did not take into consideration last week. And that what we need to take into consideration is this. Substances can change its state into three different things. It can either be a solid, it can either be a liquid, or it can be a gas, right? The difference in the arrangement and the movement of molecules among the three states of matter shows that there are stronger molecular bonds in solid than in liquid and gas. I think you already know this. You've learned this since forever, right? As gas molecules move freely at random, the bond between gas molecules is the weakest. So you already know this, right? When something is a solid, the bonds or the connection, I could say, the bond between the different molecules are strong, and so they don't move about very easily. And then when it changes to a liquid, the bonds become weaker and now it's able to move more, a little bit more freely. And then when it turns to gas, then the bonds between the molecules are very weak and it can just move anywhere in any direction. Right? So what's happening is I'll show you the graph later, and then I'll talk about what's happening. So during changes in this phase of matter, for example, when something is melting or when something is boiling. So for example, when melting is when a solid turns to liquid, and boiling is when a liquid turns to gas. What happens is, even though you continue to supply energy, right? Even though you continue to, I guess, use fire, the temperature does not change. For example, we know that water boils at 100 degrees Celsius. And no matter how long you try to boil that water, the water is not going to get any hotter than 100 degrees Celsius. That does not mean that the energy stops, So we cannot use the formula that we learned last week. Because last week we assumed that the temperature is increasing, it's always increasing. And so it's easy for us to calculate, okay, for 1 kilo of the substance, it increases by 1 Celsius, we know it uses this much energy. But now we have a situation where, one, the temperature does not change, but the energy continues to be applied or be absorbed. And so we have to use a bit of a different concept to learn this. So heat is still being continued to being applied. So this heat that is absorbed during the melting and boiling without change in temperature, this is what we call latent heat. So this is different from specific heat capacity. So latent heat, all right. So specific heat capacity is this: the amount of energy to increase 1 kilo of the substance, to increase the temperature of 1 kilo by 1 Celsius as specific heat capacity. Latent heat is this: how much energy it takes to take 1 kilo of the substance and change it from one state to another. For example, 1 kilo of liquid to change it into gas. How much energy does it take to do that? So that's a different calculation. So for example, during condensation and freezing, latent heat is released without temperature change. Okay, so it happens both ways. So either when you're melting or boiling, so either from solid to liquid or liquid to gas, it's absorbing heat, right? Even though the temperature is not changing, it continues to absorb heat until it completely changes state. Okay, the opposite happens when it's condensation or freezing. So when gas turns to liquid or liquid turns to solid, it's the opposite. It's releasing the heat. So it needs to release the heat to change state. All right. I think when you see the graph, it'll be easier for you to understand. Okay, so the quantity of heat needed to change the state of a matter of an object depends on the mass of the object and its material. Of course, makes sense. The more substance you have, the more energy it takes to change it from liquid to gas or any other states. And of course, the material, just like specific heat capacity. All right, so this is what I was saying just now. So specific latent heat, or L, of a substance is the quantity of heat. So we use Q. In the video, we use E. E stands for energy. Q is, I guess, quantity of energy. It's a similar thing. So Q, quantity of heat that is absorbed or released. You have to read the. By the way, when you read the questions, read carefully if it's absorbed or released. If it's absorbed, then it's usually either from solid to liquid or liquid to gas because you absorb heat to change. If it's released, then it's usually from gas to liquid or liquid to solid. So, is the quantity of heat that is absorbed or released during a change of phase of 1 kilo without any change in its temperature. So when it's turning from liquid to gas or gas to liquid or whatever change, the temperature always remains the same. Right? So we're calculating how much energy it takes for it to change, not how much energy it takes for it to increase, because it's not going to increase. If we look at the graph, okay, I thought the graph was on the next page. So this is the formula. So an object of mass m absorbs a quantity of heat q during a change of phase. Therefore, specific latent heat of the substance of the object is L equals q divided by m. So L is the specific latent heat. Q is the quantity of heat or quantity of energy. M is the mass in kilograms. And so we have the SI unit. So SI unit for specific heat, latent heat is joules per kilogram. All right, so there are two types of wait. Okay, so there is a mistake here. All right, let me start with this one. So there are two types of specific latent heat. So every substance usually has two specific latent heats. The first one is specific latent heat of fusion, right? So specific latent heat of fusion, or LF, of a substance is the quantity of heat that is absorbed during melting, right? So how much heat does it need? How much heat do you need to absorb to melt, or how much heat do you need to release in order to freeze 1 kilo of the substance without any change in temperature? So if it's either, so whenever the question involves a liquid and solid or solid to liquid, then you know that you're going to use specific latent heat of fusion. Then the other one is specific latent heat of vaporization. All right, I made a mistake in the description here. So specific latent heat of fusion is the quantity of heat, of vaporization, specific latent heat of vaporization, LV, of a substance is the quantity of heat Q that is absorbed during not melting but condensation, or the quantity of heat released during not freezing, but that is absorbed during either condensation, not condensation, boiling, when it turns from liquid to gas, or the quantity of heat released during condensation, when it goes from gas to liquid. So for vaporization, it's any question that has to do with either gas turning to liquid or liquid to gas. All right, so now finally we're going to look at the graph. So if we were to heat up something and we go from solid all the way to liquid, then we would be able to see a graph that looks something like this. So one is heating curve where it goes from solid to gas, and the other graph is cooling curve when it goes from gas to solid. So here's the here is the graph. So what you see here is that starting from the beginning, as you continue to apply energy or you continue to apply heat, the temperature starts to go up until you reach a point where it starts to turn from a solid to a liquid. Now at that point, now what happens is, even though you are still applying energy, the temperature does not change until all of the substance has turned into liquid or something else, depending on the type of um, substance. So during this period of changing from solid to liquid, instead of calculating using specific heat capacity, we do our calculations using specific latent heat. So it continues to absorb heat until all of it becomes liquid. Once everything becomes liquid, we can continue now. It will now continue to get hot and hot and hot and hot. And then same thing happens when you go from liquid to gas. It keeps on absorbing more and more energy, but the temperature does not go up. So more and more the energy until all of it becomes gas. And then when we turn into a gas, then finally we can go back to increasing the temperature. Uh, yeah, so very important thing, even though the temperature does not change, the energy still continues to go up. Now, some of you might be wondering, why is it the temperature does not change? So what's actually happening is that the energy that is being absorbed by the substance is being used to break the bonds. So earlier, I talked about the bonds between the molecules, right? From solid to liquid and liquid to gas. So what's happening is this extra energy that's being absorbed is being used to break apart the bonds to turn it from solid to liquid. And then once all the bonds are broken, then we can go back to increasing in temperature. Same thing from liquid to gas. So we keep on absorbing and absorbing more and more heat. Now the opposite. Okay, so yeah, so melting. So from solid to liquid, solid starts to melt. Solid is melting. You can see this in your, textbook. I can skip this. Okay, the opposite also happens when you cool down. So when you cool down something, meaning to say it's releasing energy, right? It's releasing the energy, it's letting the energy out now. So it releases energy, and as the energy goes down, it also starts to go down in temperature, right? Same thing. If it uh, releases a specific amount, it goes down a specific amount until we turn from gas to liquid. And so now it's releasing energy, and what's happening is that the bonds are starting to become stronger again. And then same thing from until all of the gas turns to liquid, then baru kita tukar lagi jadi turun begini. And then from liquid to solid, same idea, release more heat until we reach all the way to a solid. And then you can start to go on and get colder and colder until there's completely no energy left. Okay? Now, what are the effects? So, absorption of latent heat during melting and evaporation can be used to give the effect of cooling. So, uh, there are some uses for this effect that we have. So, let's talk about these two, and I'll show you some examples after this. So, absorption of latent heat during melting and evaporation can be used to give the effect of cooling. So, what's happening is latent heat, right? When there is latent heat happening, remember the temperature does not change, okay? But when it's melting or evaporating, it's continuing to absorb energy without changing temperature, which means without changing the temperature, it's absorbing energy from the surroundings. So the surroundings sometimes the surrounding starts to feel cooler because it's absorbing energy without itself becoming more hotter, right? So it gives the overall effect of becoming cooler for both melting and evaporation. So for example, melting, you put ice in a you put ice in a cup of hot water. The ice starts to What does the ice do? It starts to melt by absorbing heat from the hot water. So because it's absorbing heat from the hot water, but the ice itself still stays cold, the hot water starts to become colder and colder and colder. Okay, same thing, evaporation. On a hot day, what do? We might pour water on ourselves or we might sweat, right, to cool ourselves off. And as the water starts to evaporate to turn from liquid to a gas, it absorbs heat from our skin and we start to feel cooler. Excuse me. The opposite also happens. The latent heat released during condensation, however, is used for the purpose of heating. So let me give you an example, and maybe you've had this happen before. So if you've ever tried to get rice, maybe you're having dinner and there's rice, and this rice has just finished cooking. And so it's still hot and there's still steam coming out of the rice. Sometimes what happens is when you try to, get some rice, the steam goes to your hand. And when it goes to your hand, what happens? Your hand feels hot. Why? The steam goes from gas to liquid through condensation. But through that process of turning from gas to liquid, it releases a lot of heat. Where does that heat go? It goes onto your skin and it feels really hot. And actually, that's why steam is actually very, very dangerous. And you have to be very, very careful. Actually, steam is even more dangerous than boiling water because it actually releases a lot of heat and it releases it very fast. Right. So yeah, like I was saying, specific heat of vaporization is required in the change of phase from liquid to gas. This heat is absorbed from the surrounding. When a liquid evaporates, the liquid molecules absorb this heat to break the bond between molecules. The surrounding loses heat, therefore evaporation causes cooling to the surrounding. Yeah, so like I was just explaining earlier. So here are some examples of specific latent heat. So melting, like I was just saying, cooling drinks and food with ice cubes, right? Evaporation, so cooling body on a hot day, using cooling systems of a refrigerator also uses the idea of evaporation, and air conditioners also use air evaporations, and even sometimes of fans also use the same thing. Okay, boiling, cooling as liquid nitrogen boils, and condensation. So condensation, the idea of condensation is we take gas, and as the gas turns to liquid, the heat that it releases is used for heating things up. For example, when we're steaming food. So sometimes you put food, bila ko kasi steam food, usually steamed fish or steamed chicken. The steam from the water, even though the water is not directly touching the chicken, but the steam, when it touches the food, releases heat and heats up the food and cooks it. And when you're heating espresso coffee. So many different ways for you to use this principle. Alright, so applications of specific latent heat in daily life. Alright, so like I said, cooling system in a refrigerator. A refrigerator uses the cooling effect from evaporation. During circulation of the cooling agent, heat is absorbed from inside the refrigerator and released outside. So here we have, starting from step 1, compressor compresses the cooling gas to increase the temperature and its pressure. And as it goes up, the cooling agent releases latent heat during condensation. Okay, and then as it goes through the fridge, okay, the cooling agent evaporates and absorbs heat from inside the refrigerator. So we use the principle of latent heat to let it absorb heat from inside the refrigerator, and then it comes out and goes back to the compressor. That's why the back of a fridge is usually hot. See, at the back of the fridge, it releases heat, and then inside the fridge, it absorbs heat. Right? Evaporation of sweat, I was talking about that just now. So let's get down to how do we solve problems. Okay, examples of questions. So let's take a look at the formula that we learned earlier. So this is the formula. So I'm going to write that down on our whiteboard. So our formula is L, so latent heat over quantity of heat equals quantity of heat divided by mass, that is your specific latent heat. Okay? So let's try our first example question. This is in your textbook, so you can check your textbooks for the answer. But what I'm going to do is to show you step by step what we're going. So let's look at this first question. Figure 4.22 shows a 480 watt immersion heater used to melt ice in a container. Alright, in 120 seconds, the reading of the electronic balance decreases by 0.172 kilograms. So there are two questions here. A, what is the mass of the ice that has melted during the heating period, not heating, heating period? And the second question, B, calculate the specific latent heat of fusion of ice. Okay, so let's look at what the setup is. So what we have is we have the electronic balance to measure the overall mass. We have the immersion heater. Okay, that's connected to a power supply. We have crushed ice inside a beaker, and we have what we also have down here, a drain. So any liquid, the drain, what it does is that it lets any liquid flow out because there's liquid. So the question is, A, what is the mass of the ice that has melted during the heating period? Now, for this first question, there is no calculation, right? So no calculation for you to do. However, you do need to make some assumptions. Okay? You need to assume a few things. So sometimes when we're doing scientific experiments, we have to make assumptions. For example, what do I mean by an assumption? Okay? For example, we assume. So first we have to make assumptions. Okay, the first assumption is that we assume, or we make the assumption that all the water goes out. That all the water or melted ice, water, flows out to the sink. Or we make the assumption that all the liquid is being removed. Why is this an assumption? Kenapa why is this called an assumption? Ini tidak dinyatakan dalam soalan. It's not stated in the question that all of the water will go out. It's possible that there might be some drops that will stay behind. But because it's very difficult for us to calculate, kita kira lah semua titik-titik air yang tertinggal. To simplify it, we make this assumption that all of the water has left. The second assumption is that, and this is even more important, only heat from the heater is absorbed. I'm pretty sure the textbook uses a slightly different sentence. It doesn't really matter. You can say only heat from the heater is absorbed, or you can say the ice does not absorb heat from the surroundings, or you can say the ice only receives heat from the heater. What I'm saying is you make the assumption that all of the energy that this ice received to melt comes from the heater. We make this assumption. Now, in real life, in practical terms, this is not what happens. When you're doing a real experiment, what happens is what? The ice will not only get heat from the heater, but it will also get heat from where? The surroundings, right? The surroundings is also warmer, right? Oh, another thing you can say we assume that all of the heat from the heater goes to the ice. Again, in practical terms, that's not in reality that does not happen, because what happens is that instead of all of the water, instead of all of the heater going to the ice, sometimes some of the heat escapes to the environment. But to simplify, we make this assumption, or we make an assumption just to simplify our calculations. So you have to state these assumptions that you make. Okay, it's very important to make these assumptions, or to make this. To state the assumption. Okay, in science you can make assumptions. Okay, kamu buat anggapan sajalah. Alright, so now that you have stated the assumption, then you can answer the question. Alright, what is the mass of the ice that has melted during the heating period? Very easy. The mass of the ice that has melted is 0.172. If all of the water leaves, then and the weight decreases by this much, then we can assume that this much ice has turned into water. So for question A, we can just answer. What is the mass? So we can just answer mass of melted ice equals 0.172 kilograms. All right. Second question. So this is where we have to use the formula that we learned earlier. Now for the second question, we are still using the same assumptions, right? We still have to use these same assumptions. But I am going to just erase it now from the whiteboard. But remember that we are still using these assumptions. So now the question is, calculate the specific latent heat of fusion of ice. So LF. Alright? So what information do we already have? Okay. So we know that the formula is LF equals Q over M. Right? What is M? So in this case, we'll use M equals 0.172, like we calculated just now. What about Q? So for Q, we can use the reading of the watt. So 180 watts. So we can use the formula PT, power over time. So PT equals what? 480 watts times 120. Sorry. So 480 times 120 equals how much? It's a big number. 57,600 joules. Is that correct? Can someone double check me? 57,600 joules. Okay. So I got that correct. Okay, let me just move up everything so that you can see it in the camera. So F equals Q over M. So M equals 0.172. Q equals PT. And we know that P equals 480 and the time is 120. So 57000. Once you have all this information, like usual, just put everything in the formula, or just put everything in the calculation. So LF sorry, it should be smaller, equals Q. So we know Q is 56,000 over, we know the mass is 0.172, and you actually get quite a big number, right? If we were to calculate, or if we were to write out the full number, it would be, your textbook uses standard form, but if, let me just write down the full number. So 576,000 divided by 0.172 equals, the full number is 334,883.7 joules per kilogram. That is a lot of energy, by the way. So we're talking over 3,000, over 300,000 joules just to turn 1 kilogram of ice into water. That's a lot of heat. That's a lot, not heat, I should say, a lot of energy that's actually being absorbed. So you can see that even though the temperature is not changing, a lot of heat is being moved. That is why ice has such a cooling effect. Imagine if when something absorbs this much heat from the surroundings, there's no way that the surrounding does not get any cooler. All right. And if we were to write it in standard form, just to simplify everything, so 3.35 times 10 power of 5 kilograms, joules per kilogram. So that is your final answer for specific latent heat, specific latent heat of fusion. Now, remember this. For solid to liquid, it's going to absorb this much energy. If it's the opposite, from liquid to solid, it's going to release this much, right? So take note of that. That's very important. All right. Now, one thing you'll notice is that the tendency is that the specific latent heat of fusion and the specific latent heat of vaporization tends to be much higher compared to the specific heat capacity. It takes a lot more energy to change the temperature. It takes a lot more energy usually to change from solid to liquid or liquid to gas than it does to change the temperature by 1 Celsius. It just takes a lot of energy to do that. All right, let's try the second question. All right, what is the amount of heat supplied by a water heater to change 0.75 kilograms of water at 30 degrees Celsius to steam at 100 degrees Celsius? State the assumption you make in your calculations. All right. So what are the assumptions first? First of all, what is the assumption? Let's make the assumption. I'm not going to write down the assumption, but if you listen just now, you'd realize that the most important assumption is, again, the heat supplied by the water. We have to assume that all of the heat that the water is absorbing comes from the water heater and not from anywhere else, right? So that we can make our calculations easier. And that none of the heat is being transferred to the environment. In real life, once again, like I said, that doesn't actually happen. But to make things easier for us to calculate. All right, so it's given to us specific heat capacity of water is, again, quite a big number. So let me write that down. So specific heat capacity. So you notice they give us a specific heat capacity. And there's a reason why we're being given the specific heat capacity. And the latest specific heat of vaporization, you notice that the number is much bigger, by the way. The specific heat capacity of water to change 1 kilogram of hot water heated by 1 degree Celsius is only 4,200. But to change 1 kilogram of water from liquid to gas, from liquid to gas takes 300. If let's let me see. Am I getting this correct? Oh, it's a very big number. It's what number is this? 2 million, over 2 million joules, just to turn 1 kilo of water into gas. And it makes sense if you think about it. I mean, if you boil 1 kilo of water, how long do you have to boil it before all of it turns to gas? You have to boil it for quite a while, meaning to say it really takes a lot of energy. And that's why it's so dangerous when steam turns to water. Imagine when steam turns to water, the opposite happens. It releases over 2 million joules per kilogram. So imagine the amount of heat that comes from that steam that's being now absorbed by probably your skin. That's why even when you go and scoop out your rice, if it's hot rice, if you scoop it out too fast and all the steam comes out, you might burn your hand. So steam is actually something that you really have to be careful with. Anyway, back to the question. Specific latent heat of vaporization is given, and then latent heat of vaporization is given to be 2.26 times 10 power of 6. Now, here's the important thing. If you look at the question, there are actually two parts that we need to answer. So the first part is, let me just write everything down. So there's actually two parts. So the first part is, or the first change is, when the temperature goes from 30 to 100. Okay? So that's the first one. So change one, or part one, is from 30 to 100 degrees Celsius. Okay, the second change that we need to think about is when we go from water to steam at 100. Change 2. So we go from water to steam at 100 degrees Celsius. So this question actually has two parts. So because there are two parts, then we have to do at least two calculations. So step 1, let's see if I can fit everything. All right, so step 1, step 1. So for the step 1, we need to figure out, step 1 is to figure out how much energy does it take? How much energy does it take to go from 30 degrees Celsius to 100 degrees Celsius? That's step 1. So let's go and use the formula. So formula for specific heat capacity is what? Anyone can remember? Or do we need to go back to the formula that we learned before? What's the formula for specific heat capacity? So specific heat capacity, if you remember, specific heat capacity, C equals total energy, quantity of energy, divided by what? Divided by M, and then change in temperature. Yes, the previously learned formula. So we need to change this into, so how much energy we need to find out. So how much energy? So we are using Q instead. So we rearrange the energy. So Q equals mass, specific heat capacity, times change in temperature. All right. So how much is the mass? We know that the mass is, according to the question, is 0.75. I don't have space to write everything, so I have to simplify it. Okay. Specific heat capacity, we already know. Let me just write 4,200. That's shorter. All right. And the change in temperature. What's the change in temperature? From 30 to 100. So 100 minus 30 is what? 70 degrees. So it changes by 70 degrees. So that is the first part of the question, or the first part of the formula. And so how much is it? So let me count that. So the way your textbooks does it, it does it all in one equation. You can do that if you want. I'm just showing you how to do it in step by step, to make it easier for you to understand. So 7. So when you times everything together, and please check my answer for me, you should get 220,005. Sorry, 220,500. Please double check my answer for me. All right, now step 2. Now this is the energy you take from just to change temperature from 30 to 70. Now what we need to calculate is how much energy does it take for the water to go to steam. So for that, we use the specific latent heat. So specific latent heat we learned is what? Specific latent heat equals quantity over the mass. But since we're looking for energy, we can rearrange the formula to be Q equals mass times the specific latent heat. Specific latent heat, so we'll use the mass. So mass is 0.75. Specific latent heat is 2.26 times 10 power of 6. I'm running out of space to write, but you know what I'm talking about. And so what is our final answer? So let me write that. Let me just calculate that in my calculator. Times 10. So times 10 power of 6. So you get 1,695,000. So 1,695,000 joules. So huge amount of energy. Now, once you have the two parts, now we can just add these two. So I'm gonna just erase some of that. So total energy. So total energy or total heat supplied is 220,500 joules plus 1,695,000 joules. So you get a total of, let me just add everything. So plus 1,695,000. So you get 1.9. So 1,915,500 joules, or as usual, we can also turn this into, we can just turn this into standard form, or 1.92 times 10 power of 6. So that's how you would do it if you want to do it step by step. The way your textbook does it, it does it all in one equation. Whichever method or whichever way that you feel is more comfortable, you can do it. I would suggest, if you're not sure, to practice first doing it step by step, and then once you're comfortable with doing it step by step, then you can try do it all in one step. Okay, so and that marks the end of the topic. Now, does anyone have any questions? Excuse me. So does anyone have any chapter questions so far about this topic or the previous topic? Or about any of the formulas or any of the questions that we have done today? Or, even some other related things. Okay. If you have no questions, all right, then let me first stop the recording.